welcome everybody. I want to welcome you everybody to my presentation. My name is Kilian Michel. I'm currently working at the Department of Lake Constance Radiation Oncology Center on my master thesis about transmission detectors for online dose verification. And today I'd like to show you some interesting results of my measurements with the integral quality monitor acquired over the period of about 6 months. So the department in Friedrichshafen I'm working at had been performing its first clinical tests since September 2015 with the IQM, before I came in last year in October. Since then we've been doing lots of in-depth tests of the IQM with the main goal of its clinical implementation. And in this talk I'll address issues like the long-term signal stability, the error detection sensitivity, as well as the treatment plan verification capability of the IQM. The main feature that makes the IQM really special from other detectors is its single large area wedge-shaped ionization chamber it is based on. Here you can see what the whole thing was from the inside. And what happens is the loss of distinct spatial resolution of dose distribution, because we only have one signal per segment, which takes a little getting used to at first. And the main question I resolve within the next few minutes is why we as users can state now, based on our measurements, why the sparse information of only one signal per segment is basically enough for a sensible dose verification. So the signals are displayed within this user interface. Some of you might already know that. At the bottom we have the segment-by-segment signal, and on top we have the cumulative signal, which is basically the continuous sum over those individual signals. And the values are then compared in real time to an either measured or calculated reference that you can see in form of those green and red thresholds. If the measurement violates those error tolerances, we know that there was a clinical relevant misirradiation going on. But to date, those error tolerances have to be defined within the near future. Before we had to evaluate the performance of the detector first, and that's where the measurements I'm going to show you today come into place. The first issue we're going to have a look at is the long-term signal stability. So I measured the IQM signals of a various mixture of IMRT as well as VMAT plans over the period of about 5 months, and I compared the cumulative signals of those plans with the very first measurement. So here in this graph we can see the cumulative deviations of the values obtained at a certain day compared to the same values measured at day 0. And with the help of that graph we can observe maximum deviations of only plus minus 1%. We don't see any systematic long-term trends, and on top of that we only observe a really slight dependence of the IQM signal on the ambient air pressure. So to conclude this graph, I can say that we see a very good stability of cumulative IQM signals for the clinical use of the IQM we're applying it to. And at that point, I want to point out that a Linux maintenance here at about day 120 did not result in any significant change of the cumulative signal deviations. In contrast to that, we can have a look at the deviation distributions of the individual segment-by-segment signals of the same measurements as shown before in the cumulative manner. And on the left-hand side we have a VMAT plan, and on the right-hand side we see the measurements for a field of a IMRT plan. And here we can clearly see that a Linux maintenance led to a pretty strong enhancement in signal deviations that we can fix by just defining the measurement directly after the Linux maintenance as a new reference. Now, some of you might have noticed that the segment-by-segment signal deviations of the VMAT case deviate up to 50 or even 70%. This has something to do with the Linux-based definition of control points that relies on the application of a fixed number of monitor units. In contrast to the IQM, which relies on the gantry angle of the Linux. So there's a little bit of a conflict there, and that's why we as users decided to focus on the cumulative signal for the VMAT purposes. So now we know that the IQM solidly can reproduce its cumulative signals with an accuracy of about plus minus 1%. And in order to learn a little bit more about the requirements for the dose verification with the IQM, we did the following. So we irradiated a bunch of VMAT plants that were clinically applied at our site and set the IQM measurements as a reference. And after that we introduced some errors that were dosimetric as well as of a geometric nature. All of those plants over the course of all segments. So we opened or closed both MLC banks by 1 or 2 millimeters and compared the resulting IQM signal to the one just measured, so the reference of the original plants. Additionally, we introduced unidirectional shifts, also by 1 or 2 millimeters in both directions. And for the dosimetric errors, we kept the original MLC positions as they were and just enhanced the monitor units by 2 or 5%. So we introduced all of those 10 mentioned errors in a total number of 15 clinically applied VMAT plants. We had 5 prostate plants, 5 breast cases, and 5 plants for head and neck tumors. And the bar chart down there shows us the cumulative IQM signal deviations, the averages of those signal deviations between the measured error plan and the measured original plan. And herewith we can state that opening and closing the MLCs by 2 or 1 millimeter results in an increase or decrease of the IQM signal by 10 or 5% respectively. And for the dosimetric errors, we see a linear correlation between the enhancements of monitor units and the IQM signal deviations. But all plans involving a unidirectional shift cannot really be distinguished from the original plans. So now we have to think about how clinically relevant those errors that we introduced really are. So how much impact do the errors have in the patient? To answer that question, we can either have a look at the dose volume histograms and calculate deviations from there, or we can have a look at two-dimensional dose distributions that we calculate from all of those 165 plants and simulate our gold standard QA tool of the two-dimensional ionization chamber array within the Octavius phantom by doing that, and to calculate gamma values from that. No sooner said than done. In case of the DVHs, we focus on the mean dose within the planning target volume, and here we can see a wonderful correlation between the deviations within the dose volume histogram and the cumulative IQM signal deviations from their measured original plans. And also the mean gamma values show nice correlation with the IQM signal deviations. The bottom line of all of that evaluation of the error detection sensitivity points to the fact that the IQM is very well suited for its clinical applicability, with the main argument being that with rising deviations of the dose volume histogram, we see an increase in cumulative IQM signal deviations. And by the way, this information can also be used for the further definition of the error tolerances. Until this point, I've only been talking about the comparison between two measurements, so let's now focus on the pre-treatment or the treatment plan verification capabilities of the IQM, comparing the predicted calculated signal to the referring measurements. Over the period of about 6 months, I think, we've been using the IQM as a pre-treatment QA tool along with our 2D array within the Octavius Phantom. And within this period, we collected lots of data that we shared with IoT and then optimized the parameters for our dose engine. And this graph here, over here, with the blue bars, shows us the frequency distribution of the cumulative IQM signal deviations within the margin of -6 and 6% of the latest version of the dose engine. And here we can state that we see a pretty decent standard deviation of only 1.4%. You can think back to the long-term signal stability test that I just showed you that revealed a threshold of plus minus 1%, but we can still see a 1% baseline shift of the signal deviations compared to their calculated signals towards positive percentages, and this we interpret as a relevant miscalculations of the signals themselves, because all of the plans were indeed verified with the two-dimensional array within the Octavius Phantom, achieving a gamma passing rate of minimally 95%. And herewith we reach the conclusion of our findings. The IQM absolutely has the potential to replace the 2D array pre-treatment plan verification, and with its online dose verification capability has absolutely the potential to even increase the performance of that method. We see very good dosimetric properties as well as a nice error detection sensitivity. You can think back to the wonderful graph that I showed you that correlated the dose volume histogram deviations with the IQM signal deviations. And to date, my main point of criticism is the baseline shift of only 1% within the calculated signal. But when I have a look at the trend of the performance of the dose engine, I'm pretty optimistic to see another further improvement on that account, and be able to use the IQM within the future. To give you a brief outlook on our upcoming investigations, we actually defined the error tolerances already and are testing them out with lots of pre-treatment QA. And for my master thesis, I'm actually comparing the IQM with other performances of other treatment transmission detectors. And to finalize this presentation, I want to say a huge thank you to IRT for loaning us the IQM for beta testing reasons, as well as the kind and helpful staff at the support. And I want to say thank you very much to the Lake Constance Radiation Oncology Center, especially my supervisor Marlies Pasler, for having me, as well as for supporting me well as a master student. And I want to thank you as an audience. Thank you very much for your attention. I'm looking forward to answering your questions.